STEM fans, are you ready? Let's hear it for the world-class NASA STEM Stars team. From NASA centers across the country, we present Dr. John Mather.
Hello and welcome everyone to this episode of NASA STEM Stars, where we connect with different NASA personnel from across the agency and from a wide variety of career fields to discuss how their interests and education led them to a career with NASA and how their jobs help support the current NASA missions. I'm Seth Johnson, an education specialist from NASA's John C. Stennis Space Center on the Mississippi Gulf Coast, and I will be your host today. Once again, our guest for today's episode is Dr. John Mather, the Senior Project Scientist for the James Webb Telescope. That is scheduled to be launched late next year in the fall of 2021. Our last interview with Dr. Mather on November 12th was cut short due to technical issues, but he was gracious enough to join with us again. Now, before I introduce Dr. Mather, I'd like to take just a moment to tell you about the flow of today's episode. First, you will get a chance to meet Dr. Mather and learn a little about his background, including his past work with NASA. Then he will share with us some information about the James Webb Telescope and his work on that project. At any time, if you have a question, please put them in the chat. We have time dedicated to Q&A, and we will try to get to as many questions as we can. And finally, we will wrap up by extending to you an invitation to learn more about the James Webb Telescope by playing an online game, and also tell you about what we have coming up on our next episode of NASA STEM Stars. Dr. Mather, welcome back, and thank you so much for being with us again today.
Well, thank you, Seth. Pleasure to be back.
Now, you've had quite a career working on several satellite and space telescope projects that focused on detecting and studying different invisible wavelengths of the electromagnetic spectrum emanating from space. Can you share with us a little bit about how you became involved in that field and how it evolved into a career with NASA?
Well, sure. It was a surprise. When I was a kid, I was excited about astronomy and electronics, which were just being invented at the time. Transistors were invented when I was a kid. So nothing about today was really visible to me when I was young. So I just thought science was really cool. So I grew up, let me show a couple of slides here. I show you where I came from. Let's see that one, John. Yeah, this is 1946 that's little me on the right-hand side. In 1946, the guy on the left, Lyman Spitzer, wrote a report saying we should build telescopes in space. The guy in the middle, Sir Fred Hoyle, said the Big Bang is the craziest theory. So he didn't like it, and he gave it the name, though, that confuses us all, the Big Bang theory. And there's me being born in 1946. So was right after the end of the World War II. So in the next chart, I show you where I grew up. I grew up in far northern New Jersey, a mile off the Appalachian Trail. So it was really, really country up there. And there were only a few people in walking distance of my house. But this is the view from the front yard of my house. That's a research facility down the hill. That is a barn where about a dozen bulls lived, and they were ancestors of many cows of northern New Jersey. So that was my dad's work. He studied those cows and those bulls to see if we could get better milk, which we can. So that was what research was important. That was important research in 1950s, and now we do have much better milk. So this was a place where I learned science by getting books from the library and fiddling around with a crystal radio and a one-tube radio in the house, and just trying to learn everything that I could in the countryside. So books. I read books. That's how I got started. So that was the beginning. And I went to public high school and then on to college, and finally ended up in graduate school in Berkeley, California. And if you show me next chart here, it's got a picture of the experiment that I did for my thesis. This is an experiment that was intended to measure the cosmic background radiation, millimeter waves from space. They had just been discovered a few years before that, and so, of course, graduate students should try to do a project to find out more about it. So the sketch on the left is the concept of the idea, and the concept was, well, let's launch something high up above the Earth's atmosphere, as high as we can get, to measure as though we were in outer space. So we built what I call a spacecraft on a string. And we launched it on one of these giant balloons. This is not the real one, but this is somebody else's on the right-hand side. So it went up about 25 miles to way above the Earth over Texas. And that was my start into this subject. However, it was a bad start. That payload failed to function for 3 different ways. And so I got a job at NASA in New York City thinking, well, I'll just do something completely different. And so I was there for a couple of years, but as soon as I got there, almost as soon as I got there, NASA said they wanted proposals for new satellite missions. I said, boss, my thesis project failed. We should try it in outer space. He said, okay, we'll call up our friends. We will write a proposal. And so we did. And I thought nothing will happen. But a couple of years later, I was invited down to Goddard Space Flight Center in Greenbelt, Maryland, where I still am. And the idea was to actually figure out how to do that project. And so that's how I got started.
So,
do we have any questions, Seth, yet?
I don't see any posted in the chat right now, but I've got a question. It said your original project failed by launching it into a high altitude, trying to get it above as much atmosphere as you could. Did you kind of know right away why it failed, and you thought that by placing it in space in orbit would make it work, or did you just have a hunch that it would work better being that high up, or how did that transition go?
Well,
failure and rethinking your idea.
Well, sure. The first failure was just a failure to function properly. There were lots of reasons that it didn't function, and we didn't know that until after we got it home and could analyze it and test it. So, however, actually my fellow graduate students and advisors did actually fix it. And I made it work the second time. It worked perfectly the second time. So we knew it was a good idea.
Okay.
So that's how that one got started. Well, why don't we show the next picture, because it'll show you what we did with the idea. So in 1974, we drew a sketch on a napkin that looked like this. And in 1989, we launched it. Actually, just the 31st anniversary was just this week, November 18th. So anyway, there it is in outer space as seen by the artist. And it has instruments to measure the heat of the cosmic background, the leftover heat from the Big Bang itself. So 3 instruments in there. 2 of them were for that purpose. One of them was to look for the light of the first galaxies. And it did work, because real engineers knew how to make good things that worked a lot better than a graduate student can do. And so within weeks, we had our first result. And so I want to show you that on the next picture there. This is a picture of what's called the cosmic microwave background spectrum. That curve there with the little dots on it is the first measurement we got. I showed this to the Astronomical Society in January of 1990. We got a standing ovation. Probably the first time that a curve got a standing ovation. So what did it mean? It meant that the Big Bang story, which is confusing everybody, is basically correct. Was the only story that we have that could explain the perfection of agreement between the theoretical smooth curve and the actual measurements. So that was the beginning. A couple of years later, we made another discovery. We mapped the sky and said, well, it's not really equally bright in all directions. Some parts of the sky are brighter than others, and this is due to something in the Big Bang material itself. So now we know that that's really important to us, and it's been followed up by 2 other satellite missions, as well as lots of people on the ground. So after all that, we got to go visit the King of Sweden there in Stockholm in 2006. So our ambition, our experiment turned out to be a good one. You never can tell at the beginning. You could perfectly well imagine your rocket will blow up on the launch pad, because that can happen, or that your equipment isn't going to be quite what you hoped it would be. or that nature just doesn't cooperate with your opinion. But at any rate, it did work, and there we are having a diploma from the King of Sweden. So that's how I got into my world. But that was a long time after the launch. So anyway, so that's how I got started. Yeah. Any more questions come in yet, Seth, that we should think about?
Let's see. I see someone is typing right now, but in the meantime, could you tell us a little bit more about that meeting with the King of Sweden and what that entailed? A little more about that.
Oh my goodness! Yes. Well, suddenly you're a famous person, and everybody knows who you are. You're walking down the street in Stockholm, and people know you're there for a reason. You get a diplomat to accompany you. You get a car and driver. And you have 10 days of parties and speeches celebrating the great accomplishment. So, of course, now, I had to explain what we did. Yeah.
Is the Nobel Prize itself, is it a medal? Is it a trophy? It was kind of obstructed in the picture. What?
Okay, well, the Nobel Prize is a little gold cookie about that big around, and it's quite heavy. So it does not come on a little string. You do not wear it on your neck.
It doesn't make a good keychain?
No, it's not a good keychain. But what they have instead is they have chocolate-covered Nobel medal cookies that you can eat. So those were lots of fun. It's a very, very intense party, including a banquet with the king and queen. I get to talk to the queen. Well, what's your world like? What are your kids up to? Things like that.
Great. Well, we have some questions from some of our viewers already, and it says, what is the purpose of the James Webb Telescope?
Okay. Well, why don't we start talking about that one then? The purpose of the James Webb Telescope is to extend all of the discoveries of the Hubble Space Telescope out into greater distances, farther back in time, and to look at the things that the Hubble can't see because it doesn't see at the right wavelengths or it's not big enough. So why don't we show the next chart? I'll explain this a little bit. This is one of the most famous pictures from the Hubble Space Telescope. And what you see here are about 1,000 galaxies and 2 stars. And so if you point the Hubble telescope at an empty place in the sky where there's almost nothing that you know about, and you do a time exposure for a couple of weeks, this is what turns up. The little fuzzballs there are each one a galaxy. And the redder ones are red because they're far away and the universe is expanding. So these all are running away from us at great speeds. So astronomers looked at this picture and they said, that is wonderful. We are so proud to have this picture. And by the way, it's not enough yet. Please build us a more powerful telescope that can see farther than the Hubble. Farther because the things we need to see are fainter and their wavelengths that they're sending to us are longer than what the Hubble can pick up. So please build us another better telescope. So that's the big reason for why that picture was so important. And the next picture shows you another piece of what's important about the Webb. This is the Eagle Nebula. This is a place where the nearby material in our own galaxy is forming new stars. And you see there, this beautiful cloud, the stars are actually being born inside the parts that are hidden by dirt and by dust in space. So astronomers would really like to know how stars are formed. And it would be great if we could see inside those clouds. So if we said, well, okay, infrared wavelengths are longer than regular wavelengths, visible wavelengths, and they can go around the dust grains and see inside, let's try some of that. So the next picture shows what happens with even with a Hubble if you can go to a little bit longer wavelengths. And this shows that the dust becomes less opaque. You can begin to see through the clouds and see inside where the stars are being born. So where did everything happen? How did the galaxies grow? How did the stars grow? How were the planets formed? That's all what we wanted to find out from observing with a Webb telescope. And what's different and better and important for us is the telescope is bigger and is designed to pick up infrared light from things that are much further away or much colder than what you can see with your own eye. So please fill in the entire history of the universe from the Big Bang till now by observing everything that you could see with this new equipment. And by the way, it is so incredibly powerful. If you were a bumblebee hovering out there at the distance of the moon, and you would sit still for a while, we could take your picture. We could see you were a little dot out there against the sky in two ways. One is the sunlight you would reflect, and one is the heat that you would radiate, which we would pick up as infrared light. So we sort of know if you build something this much more powerful than anything we've ever had before, that it will be exciting. So we're expecting some surprises to turn up, as well as everything I just told you we are hoping for. So that's what we're trying to build it for.
Sure.
Any more questions come in yet?
Yeah, we have, why is it named the James Webb Telescope?
Oh, James Webb was the second administrator of NASA. He was the person who figured out how we should go to the moon with the Apollo program, and worked with our whole agency to figure that out, and with contractors around the country. And eventually 500,000 people worked on the Apollo program. And that was a huge accomplishment. Along the way, he also said, Mr. President, we should do some science. Please let us set up some science laboratories. Please let us start exploring the solar system. Let's send out probes to Mars and to Jupiter, Saturn, Uranus, and Neptune. So under James Webb's watch, we did all those things. And so this is the first time NASA's ever named a science mission after one of its own administrators. But he was a brilliant one and very well worth making that recognition. So thanks for the question.
Yeah.
He was awesome.
So I know you've got some more slides about the James Webb Telescope. A couple of the questions that we have, I think, will be answered through that.
Okay.
One being, we know that the Hubble telescope was made as large as could be launched in the payload bay of the space shuttle, but how are you going to make a larger telescope that can still launch on a rocket?
Oh, my goodness. Well, it will have to fold up and then be unfolded after launch. So we do have a few pictures and a movie to show you about that. Let's jump to the next picture, which will show you how big it is. This is a couple of hundred of our team members out of several thousand who worked on the project, and that shows you how big the telescope it is. It is much, much larger than the rocket could ever be. Much larger than any rockets it's much larger than any rocket we're even thinking about building. So this is not the real thing. This is just a steel model so we can show off to people. But that giant golden hexagon is what's going to collect the light from the distant universe and focus it down on a detector. So, and then I want to show you in the next chart something about it. This summarizes the groups that are working on it. NASA is doing it along with the European and Canadian space agencies and a company called Northrop Grumman Aerospace Systems. Mostly they're located in California near Los Angeles Airport, not too far away. And we have instruments coming to the telescope, or they have already come to the telescope from all around the world, from University of Arizona, from Europe, from Canada, and various contractors in the US. We will be operating this the way that we do with the Hubble Space Telescope. There's an institute in Baltimore called the Space Telescope Science Institute. We will have our people up there sending commands to the observatory and receiving the data back. And if you're an astronomer, this is the week that you are writing proposals to be able to use this telescope. Please tell us why your favorite targets are the ones we should be looking at and what you're going to do. By the way, it's planned for launch, if we're lucky still, as we've been lucky lately, in October 2021. And it will be launched from French Guiana in South America, because the European contribution includes the rocket, which goes from French Guiana. So now I want to show you how we put it together and what it takes to get from idea to launch. So in the upper left corner, we see the big telescope as it was assembled at Goddard Space Flight Center. Then the next picture to the right is the telescope surrounded by a plastic tent and being placed on a gigantic shaking device so we can simulate the launch that it will face. Then after that, we put it in a shipping container, put it in this airplane called the C-5C, and we fly it down to Texas to the Johnson Space Center, where we have a totally gigantic vacuum tank, which was used by the Apollo astronauts themselves to practice getting out of their capsule onto the moon. We flew it from there to Los Angeles, where it now is, and we're finishing the tests and assembly there. So the one last thing we have to do is to unfold it one last time and fold it up one last time, and then we ship it through the Panama Canal to French Guiana, put it in the giant rocket that they have, but it's still a folded up telescope, and then we launch it there and send it up into space, and then it will become the telescope in space. So the picture that I want to show you after that is our movie that shows you how it will unfold in outer space. And so this partially answers the question of how a telescope so much larger than the rocket can actually work. So here we go. This is a much faster than the real thing animation. Actually, we have 2 weeks to accomplish what we're showing you in this movie. This is an extraordinarily complicated thing, and you could say, well, why is it that complicated? And the answer is, it's the only way we can do it. We need a very large telescope to see these most distant objects, and it's got to be folded up. So as it unfolds in space, we will watch every move that it does. There will not be a human being out there, but there will be sensors on the bird that will tell us how it's doing. And if anything doesn't work perfectly, we have another way to try everything. So that's called redundancy. We have 2 of every kind of electronics that we need, and we have a lot of ways to accomplish things that might go wrong. So that's how it goes into space. So that is what will enable all these wonderful discoveries, to see if we can see how did we get here from the Big Bang, from the first galaxies to the formation of stars and planets. And we'll even be looking at some nearby planets to see what are they like. A hope is to find something sort of like Earth and find some evidence about that little object. So, more questions come in, Seth?
Yeah, that the telescope is a reflecting telescope, and this is my own kind of personal question. I have a 12-inch reflecting telescope that I pull out from time to time, and sometimes if it's been a couple of years and I bring it quite a few distance, things aren't lined up they need to be, and I need to readjust everything, get it aligned. They call that collimating. With this large telescope unfolding in space, is it able to adjust and align itself, or is it just made to do it right the first time? Is it something that can be constantly changed and refocused, and because I know it's going to be in a place where we're not going to be able to send a manned crew like we did with the Hubble to repair and refurbish?
Well, a good question, because that was our first question. How are you going to adjust and focus this telescope after it's launched? And the answer is, all of those mirrors have motors on them to move them around as needed. And so what we see when we first launch it is we'll pick up 18 different images of a single star, because each one of those 18 mirrors is going to be pointed a little bit differently. So we have a process we developed that will enable us to focus them up as though they were pieces of one giant mirror. So it will be focused as needed, whenever needed, but probably every week or 2.
All right. So here's a question we have from the chat. It says, is the blue light spectrum significant to physicists as it is to biologists? So I'm not terribly familiar with biology, but...
Yes. Well, the answer is absolutely yes. The Webb telescope is designed to pick up light that begins around the red wavelengths and goes longer. But in truth, we're looking at what we call red-shifted blue light. The distant universe is running away from us very fast, and that means that the wavelengths that we receive are much longer than the wavelengths that were sent out. So we're actually observing the blue and ultraviolet light from the most distant galaxies with our infrared telescope. So yes, we care very much about that blue and ultraviolet light.
So that shift, that red shift due to objects, traveling away, shifts it that much that it changes the spectrum of light that it emits?
Tremendous change. We think we can see objects that are running away so fast that the wavelength that we get is 10 or 20 or maybe even 30 times longer than it was when it was sent out. So this tells you that we're going to be able to see within maybe 100 million years of the Big Bang itself. So that is something nobody has ever been able to do before with a telescope. Although, to tell the truth, that cosmic background radiation that we measured with the COBE satellite, we see it as it was only 400,000 years after the bang. Yeah. But no objects, only hot and cold blobs in that picture.
So, and we'll be able to see images sort of in the same way that we do with the images from the Hubble Space Telescope, where they kind of falsify some of the color just so that we can still, at least, I know you'll have plenty of data, but that we'll be able to visually see how remarkable these images are.
Oh, yes, absolutely. We will turn the electronic bits into color pictures so that you can see them. Of course, the human being could not see any of that infrared light at all, so we have to pretend a little bit. But we have a system. Basically, we usually put the shorter wavelength as blue, middle wavelength is green or yellow, and then the longer wavelength is red. So when we show you a picture, we know that you can sort of interpret it as though it were real. Because we don't want to confuse people. We need it to be something you can understand.
Okay. And let's see, we have one final question. It's a little bit of a physics question, but maybe you'll be able to handle that for our viewer. It says, can we use a concept of a slingshot after the launch of rockets to help with the help of a big parachute?
We don't currently use sort of thing that looks like a spring as a slingshot. We do use springs sometimes to help separate the parts of a rocket. When the payload separates from its rocket engine, they need to get apart without hitting each other. So we use sometimes springs for that. There's another thing that we do, though, that's called a gravitational slingshot. If you want to go faster, sometimes the thing to do is fly past another object, like the moon or another planet, and pick up some energy from its gravitational force. So that's called a gravitational slingshot. We do that. In fact, we did that very effectively when we sent the probes out of the solar system under James Webb's leadership. They went past Jupiter, Saturn, Uranus, and Neptune, and they all got more, and it got more energy from doing it every time. So
just getting a free
special
assist.
Discovery. Free assist, free extra energy from a planet.
Yep. And we did have one more question. I think this will be the final question, and this is really interesting. So where will the James Webb Telescope orbit? Where will it be located out in space?
Okay. We are putting it around an area called Lagrange Point 2, which is about 1 million miles farther from the Earth, from the sun, than we are. So it's a place that goes around the sun with the Earth every year, and the telescope orbits around that area. So it stays near us, does not continue to escape, but is almost as far away as it could be without escaping. So we keep it there. It's a perfect place because from there, looking back towards the sun and the Earth, the Earth, the moon are all hidden by the sunshade. So the telescope is in the dark. We need that.
Yep, that's good for being able to collect all that faint light coming from other places. Well, Dr. Mather, thank you so much for being with us here today, especially second time around, and being able to tell us a little bit about yourself and about the James Webb Telescope. Right now we want to extend an invitation to all of our viewers that we have another resource for you to get more information about the James Webb Telescope and to play an online game. We've got if we can bring that slide up with that web address for everyone to be able to see. It's called the Scope It Out game, and there is the web address where you can find it. And when you play this game, you can share your score on social media at #NextGenStem. And we want everyone to subscribe to our NASA STEM Stars channel and tune in for our next STEM Stars episode, who will be Dr. Georgia Dinolfo, with a topic about heliophysics, and that is going to be next Thursday, December 3rd at 2 o'clock Eastern Time. Once again, I am Seth Johnson and want to thank all of you for participating with us today. Another thank you to Dr. John Mather, and thank you all for participating, and we'll see you on the next NASA STEM Stars.